So in this video, we're going to be talking about cylindrical coordinates, which is an alternate coordinate system for describing points in 3D space. So usually we use rectangular coordinates, which of course describe a point using the x, y, and z coordinates. And rectangular coordinates are nice and all, but sometimes they're a little too rectangular. To show what I mean, say we want to describe the unit circle. Now, in rectangular coordinates, the equation is going to be x squared plus y squared equals 1. But if we use the polar coordinates, the equation simply becomes equals 1. So the equation for the circle in polar coordinates is much simpler than in rectangular coordinates. And so it's going to be the same idea for cylindrical coordinates. You're going to find that it's much easier to represent certain curved objects in cylindrical coordinates as opposed to rectangular coordinates. So to describe a point in 3D space using cylindrical coordinates, we use three parameters: theta, and z. So you can see that cylindrical coordinates are really just an extension of polar coordinates into 3D space, because and theta mean the exact same thing. Is the distance of the point from the z-axis, and theta is the positive counterclockwise angle it makes from the positive x-axis. And then the z-coordinate is just the same z-coordinate as in rectangular coordinates. So basically, and theta are the polar coordinates of the projection of the point onto the xy plane. So you can think of it as you describe the point using polar coordinates in the xy plane, and then use the z to describe the height above the xy plane. And the reason it's called cylindrical coordinates is because the equation of a cylinder is very simple. If we have equal to the radius, then it describes a cylinder of that radius around the origin, because those are all the points equidistant from the z-axis. And since theta and z are not in the equation, it works for any value of theta and z. And so since cylindrical coordinates are just an extension of polar coordinates, the equations to convert between the two are the same. So just like polar coordinates, we have x equals cosine theta and y equals sine theta. And then of course z is the same as in rectangular coordinates. So say we wanted to convert the point 3 pi 4th 5. So first of all, let's make a rough sketch of the point. So we go to the angle pi 4th from the positive x-axis, move forward 3, and then up 5. Okay, so it looks something like that. And then to convert, we simply use the formulas. So this is the coordinates of the same point in rectangular coordinates. So lastly, let's look at a couple examples of surfaces using cylindrical coordinates. So say we have the unit sphere. To convert to cylindrical coordinates, we simply replace the x squared plus y squared with squared. Of course, we know that relation from polar coordinates. Say we have this equation z equals So this equation is already in cylindrical coordinates, and we want to find the same equation in rectangular coordinates. So if you square both sides, and then replace the squared with x squared plus y squared, you can see that it's an equation of a cone.